All of the circuits we've talked about so far have been constant in time. Um, Notice there's never any t in the equations that we calculate. If you have a certain battery voltage and you have a certain set of resistors, then just forever until the battery dies, the current and the voltage are going to be the same. Now we're going to talk about circuits that have capacitors in them. And for the first time, we're going to see a dependence on time. So when you have a capacitor and a resistor in series, and in some cases, sometimes a battery, we'll talk about when. This also has to be in series. You get time dependence. You get current values and voltage values that change over time. So your current will be dependent on time, and your voltage will be dependent on time. And we're going to break this down into two different cases. So we know that capacitors you can charge a capacitor, and then after the capacitor is charged, it can deliver current to other elements. So we're going to break it into those two different cases. The first one is if you connect to a battery to charge the capacitor. Then you have something like this. I'll put the battery down at the bottom, the capacitor over here, the resistor here. Okay, so this is a case, and notice these are all in series because each pair of these adjacent elements shares one node and nothing else shares that node. And so the battery charges the capacitor, and the resistor affects how quickly that charging happens. So this is one case we'll consider. And the other case we'll consider is now if you disconnect the battery, then you get discharge of the capacitor. And so that battery won't be involved, and you just have a capacitor and a resistor in series. Now, in practice, a lot of times you'll use a switch to go from one case to the other. So we can change from one case to the other using a switch. And so here's an example of what that could look like. So say we have the battery down at the bottom. And then this is the switch. And then, so the switch, the way I have it drawn here, is not connected to anything. And we have the capacitor there, the resistor there, and then we have another wire going like this. And so let's call these two terminals A and B for the switch. Okay, so the way it is right now with that switch gate not touching A or B, we don't have any circuits. So nothing's happening here. If this capacitor is charged, it's just staying charged. No electricity can go anywhere. If you throw this switch to A, okay, let me draw a line there. So now that gate is like this. You can see that there's a circuit that goes around. No current goes to B here. And so now this battery can charge the capacitor. Okay. Once the capacitor is charged at the level that you want, you can move this gate to B. And now notice that the battery is no longer in a circuit. So no current flows in the left part of this. Now all that you have is a circuit on the right half of this. And so this capacitor is no longer being charged. It's discharging the charge that it's developed by being hooked up to the battery through that resistor. And so those are the two cases that we're going to deal with. It's just another way of representing these two cases that I gave you above. Okay, so when this resistor and capacitor are connected to a battery, you get charging. The capacitor is developing charge. And there are two kinds of equations that you're going to use. And this is true for the charging and the discharging. We're going to want to be able to calculate at any given time how much charge is developed in the capacitor. So I'm going to call that lowercase q. And this is equal to the capacitance times, I'm going to use the EMF symbol for the voltage for all of this. And so that's what this epsilon represents, is the voltage of the battery. I guess I'll put that in this one too. So remember, that's the EMF. And the charge at any given time is the capacitance times the voltage, or the EMF, times the quantity 1 minus e to the power of negative t over RC. And another way you can write this is since the maximum charge you could develop with a capacitance C and an EMF of epsilon is, we'll call it Q max, and it's equal to C times epsilon. You can write this also as the maximum possible charge times the quantity 1 minus e to the negative t over RC. Okay, that's one thing that can sometimes be desired to calculate. The other thing is calculating the current in this loop. And remember, since everything's in series, the current in every element has to be the same at all times. Okay, so we're gonna, you can think of this as the current going into the capacitor, but it's also the current in the resistor and the current leaving the battery. And this current, as a function of time, is equal to the EMF divided by the resistance of the resistor times e to the power of negative t over RC. Okay. And if you plot out these functions, what you get is charging over time that looks something like this. So if this line is the maximum possible charge, that's C epsilon, or also Q max possible. You get a curve that looks like this, and it asymptotically approaches that maximum possible as time goes by. And if you want to think about how the current changes over time, the current starts out at its fastest, and then as the capacitor is charged, it slows down towards a current of 0. Okay, and this maximum value of the current is the voltage over R, which, according to Ohm's law, is the current that you would get if there was no capacitor and there was only the resistor. So at the very start, the current behaves as if that capacitor isn't there. But little by little, as the capacitor fills up, that current slows down. One important thing in charging and in discharging also, is what's called the time constant. And we'll use the Greek letter tau for that. And the time constant is equal to RC. You can see that that comes up in these equations in the exponent for E. And one important thing about the time constant is after an amount of time that's equal to tau, equal to RC, the charge in the capacitor when it's charging is 63% of its maximum possible. And the current is 37% of the maximum current, which is the voltage over the resistance. Okay, so you can see that after one time constant, we've gone a considerable way towards getting this capacitor all the way charged. We're not all the way there yet, but we're 63% charged, and the current is slowed down to 37% of its original. Okay, so the equations that are important here are these, and then remembering what that time constant is. Okay, so now what about when it's discharging? So now you remove the battery, and in a way you use this capacitor as, it's like a battery kind of, although it doesn't behave just like it. It does produce current on its own. And we want the same things for the discharging capacitor. So the equation for the charge in the capacitor is the starting charge. Now this isn't necessarily Q max. This is just whatever value that it's charged to times e to the power of t over RC. And the current that's produced from this discharging capacitor is the starting charge divided by the time constant times e to the power of negative t over RC. And notice that this current now is in the opposite direction that it was going when the charging was happening. I'm not giving you problems that emphasize the direction on this really, but I'll put a note in here. So this is in the opposite direction, this current. When it was being charged. Okay, so here are the two equations that you want for a discharging capacitor. And what is it about the time constant here? So after an amount of time RC, Q, and well, this Q value is 37% of its starting value. And I is 37% of its starting value. That starting value being at time equals 0. Okay, so let's see how we use these in a problem. So let's say we have a circuit. I'm going to use the switched setup. Okay, so that's what the circuit looks like, and I'll call this position A and this position B for the switch. And the battery has an EMF of 20 volts. The capacitor has a capacitance of 1 times 10 to the minus 6 farads. And the resistor is 2,000 ohms. And so let's say that the capacitor is uncharged at the instant the switch is thrown to position A. Then after 2 times the time constant, the switch is thrown to position B. And we want to calculate two things. We want to calculate the current and the voltage in the resistor while it's charging. And these are both going to be functions of time. And then second, we want to calculate the current and the voltage in the resistor during discharging. And really, you know, this is just about using those 4 equations that I gave you. In this case, we're not asking for charge. Well, we are going to, in second thought, we are going to have to use one of the charge equations at one point to see how much it's charged after 2 time constants go by. Okay, so let's get into it with the case where it's charging. So we are going to say I, as a function of time, is equal to, here's the equation I'm using, the EMF over the resistance times e to the negative t over RC. And if I put these values in, we get 20 over 2,000 times e to the negative power of t over the resistance times the capacitance and this comes out to be 0.01 e to the negative 500 t. Okay, so that is the current in the capacitor. And since all of these elements are in series, they have to have the same current. That's always true of things. Any two things that are in series have to have the same current, although they can have different voltages. And so now how are we going to calculate the voltage across the resistor? Well, remember, we're going to use Ohm's law. That always dictates what happens in resistors. And Ohm's law says the voltage across the resistor is equal to the current times the resistance. So the voltage as a function of time is equal to the resistance times the current we just calculated. And so you get 20 times e to the negative 500 t. Okay, well, so what's happening here with the voltage across the resistor as this charges? When t is equal to 0, e to this exponent is equal to 1. You have e to the 0. And so right at the start of charging, we have 20 volts across the resistor, which makes sense. It's sort of like the capacitor isn't there. Then little by little, e to the power of this thing as t gets bigger, what we get is that the voltage goes down over time exponentially. Okay, so now for part B, now we want to calculate I and V in the resistor during discharging. Well, we can't do that until we know what the starting charge is. So we're told that the switch flips. Hold on. Okay, so we're told that the switch flips to B after 2 times the time constant. So what we want to know is what's the charge in the capacitor after 2 times the time constant. So we're still going to use the charging equations to figure out what the charge is at time 2 tau, or 2 times RC. Okay, so the equation for charging says Q as a function of time is equal to C times epsilon times the quantity 1 minus negative T, whoops, I didn't put the E in there, 1 minus E to the power of negative T over RC. Okay. And now we can put the values in. So the capacitance times the EMF comes out to be 2 times 10 to the minus 5. And then we're multiplying that by the quantity 1 minus E to the negative 2 RC, that's our time, divided by RC. Okay, that's the exponent. And so what we get, the RC's cancel out in the exponent, and you get 2 times 10 to the minus 5 times the quantity 1 minus e to the negative 2. And we get a value of 1.729 times 10 to the minus 5 coulombs. Well, the maximum charge that this circuit could develop in the capacitor is C times epsilon. And so that would be 2 times 10 to the minus 5th. So you can see this is how close we got to fully charging this capacitor after 2 time constants go by. Pretty close, but not all the way there yet. And it'll never get exactly there, but it'll get very close if you let it run for 4 times the time constant or whatever. And this time constant for this circuit is very small, so it doesn't take very long for it to get close enough that you can just basically treat it like it's fully charged. Okay, now that we have that starting charge, we can use the equation that says during discharging, the current is equal to the starting charge divided by the time constant times e to the power of negative t over RC. And so let's put these values in. Our starting Q is what we just figured out. So 1.729 times 10 to the minus 5 divided by RC, which is 0.002, times e to the negative. We already figured out before that 1 over RC is equal to 500, so this is minus 500t. And if I just figure out the coefficient, this comes out to be 0.008647 e to the negative 500t. That is the current coming from the capacitor, but since these elements are in series, that's also the current going through the resistor. And so to find the voltage across the resistor, again, we're just going to use Ohm's law. And so Ohm's law says that the voltage is equal to the current times the resistance. So the voltage across the resistor as a function of time is equal to 2,000 times the current. And we just figured out the current function. So this gives us 17.29 e to the negative 500t. So we're starting out with a voltage across the resistor of 17.29 volts, and then we're decreasing from there as time goes by. Well, what can you do with this if your capacitor and resistor, let's say that you have more than one capacitor, is there anything you can do with that? It turns out that there is, if we use the rules of series and parallel capacitors. So far, we've only talked about a single capacitor. But you can replace multiple capacitors by a single capacitor if you use the rules of parallel and series capacitors. So you can treat multiple capacitors as a single capacitor if you use the rules of series and parallel capacitors. I talked about something like this with resistors. You can also do it with resistors, and I want you to notice that the rules are switched for capacitors compared to resistors. And you'll see what I mean as I get into this. So, okay, if you have two series capacitors, remember the definition of two things that are in series is that they share one node and no other element shares that node. So this would look something like this. And let's say this is C1 and this is C2. Okay, that's two capacitors, but you can imagine wrapping this up in electrical tape and packaging this whole thing as a single capacitor. Okay, and let's say that we would call this capacitor C equivalent. Okay, so what's the capacitance of this combination? What's the capacitance C equivalent? The easiest way to remember it is 1 over C equivalent is equal to 1 over C1 plus 1 over C2. But that's not the way you would do the math. To do the math, you would have to get a common denominator and then flip it with the reciprocal. And what you get is that C equivalent is equal to C1 times C2 divided by C1 plus C2. Notice that this is the relationship. This is series capacitors, but it has the same relationship as parallel resistors. So that's what I'm saying when I say it's kind of the backwards relationships, and you need to remember that. And now what about parallel capacitors? Remember that the definition of two elements being in parallel is that they share nodes on both sides. And other things can share those nodes too. By the way, any elements that are in parallel have to have the same voltage. And any elements that are in series have to have the same current. Okay. Okay, so what would this look like? Something like this. Here's C1, here's C2. And again, you can imagine you have this great business idea where you buy two capacitors and then you sell them as a single capacitor. I don't know if that would make you much money, but you could do that, you know. So this thing circled in green is a single capacitor on its own, and it has the value C equivalent. And in this case, C equivalent is just the sum of C1 and C2. Okay, so let's put this into a problem. Let's say we have, we're only going to think about the charging in this case. There's no reason, I mean, of course you can do this exact same thing while it's discharging, but I'm going to just do the charging part. Okay, so here's our circuit. And I was going to, I'm going to put one more capacitor in. So let's say that the top one has a capacitance of 3 times 10 to the minus 6 farads. The one below on the left has a capacitance of 2 times 10 to the minus 6 farads. And then the last one has a capacitance of 1 times 10 to the minus 6 farads. And the resistor is 500 ohms. And the battery is 50 volts. So the EMF is 50. And let's say that as this charges, we want to know what's the current and the voltage in the resistor. Well, as this problem is right now, we can't apply any of our equations for the current or the charge as this thing charges. But what we're going to do is we're going to use the fact that the two lower capacitors are in series with each other, so we can replace them with a single capacitor. And then once we've done that, the top and the bottom capacitors will be in parallel, and we can combine them into a single one, and then we can solve our problem. Okay, so the first step is I'm going to replace the two lower capacitors with a single capacitor. Okay, and we have to figure out what the value is of that lower one. The top one hasn't changed, so that's still 3 times 10 to the minus 6. Okay, but this equivalent capacitor on the lower wire is, we're going to use the formula 2 times 10 to the minus 6 times 1 times 10 to the minus 6 divided by the sum of these two. And that gives you an equivalent of 6.6 repeating times 10 to the minus 7 farads. And now we have these two that are in parallel with each other. They share nodes on each side. And so now we can simplify one more time, and we get a circuit that looks like this. All we need is the equivalent capacitance of these two that are in parallel. So this is 3 times 10 to the minus 6 plus 6.6 repeating times 10 to the minus 7. And that gives us 3.6 repeating times 10 to the minus 6 farads. And now finally we have the case that all our equations are for. We have a battery, a capacitor, and a resistor in series. And so now we can calculate the current. This is the charging case, remember. So the current is equal to the EMF over the resistance times E to the negative T over RC. And so that is 50 over 500 times E to the power of, if I simplify the math, negative 545.46 T. And then this is 0.1 E to the negative 545.46 T. And now that we have the current in the resistor as a function of time, we can calculate the voltage using Ohm's law. And so the voltage as a function of time is equal to the resistance times the current which comes out to 50 times E to the negative 545.46 T. Okay, there's just one more thing that I want to tell you, and it's really easy. So in all of these examples, I've been asking for the current and the voltage through the resistor. One thing we often want to know is the power delivered to the resistor. And that's just a calculation that involves the two things that we've calculated, voltage and current. Okay, so the power delivered to the resistor, capital P, is just the voltage across the resistor times the current through the resistor. And so if I'm going to use the example that I just did, the example above, if we want to calculate the power delivered to this resistor as a function of time, we can just take the voltage as a function of time, multiply it by the current as a function of time, And using the exponent rules, we have 50 times 0.1 is 5 times e to the negative. Here's where the exponent rules come into it. This is the same as e to the sum of those two exponents. So this is negative 1090.92 t. Or it would be easier if you were just asked to calculate the power at some instant in time. Then you'd plug in, say we wanted to know at time 2 seconds, we plug in 2 for t, calculate the single value for the current, the single value for the voltage, and then use this equation to get just a single value of the power. The units of power are, it's joules per second. And so the SI units are joules per second, and that's given its own name, watts.